Let us look at chemical bond. So now, after we've seen how atoms are built, and we know that there are outer electrons available for further interaction, we can start looking at chemical bond. This material you can find in. So where we'll be starting from? The easiest is to start with the simplest atom, which is hydrogen. It has proton inside. You cannot see the size of proton, and electrons flying at space around proton at scale 100,000 larger than proton is. Now we want to build hydrogen molecule built of two hydrogen atoms. Two of them are exactly identical. Now we remember that in hydrogen atom electron, the only electron sits at 1s orbital. At the second atom it will be exactly the same. Now we are looking for solution of Schrödinger equation for this system of two hydrogen atoms. Mathematicians say that if something is solution of differential equation, and Schrödinger equation is differential equation, then sum or difference of these solutions can be a good solution. So we will be looking at two solutions of Schrödinger equation. One will be addition of two 1s functions from atom 1 and with atom 2. And another will be antisymmetric, so addition for atom 1 and subtraction, algebraic subtraction, atom 2. So here 1s will be with sign plus, and here it will be with sign minus. In case of symmetric, this will be the result of addition, and probability to see the electron will be square of our wave function. It will look like this. Of course, square is always positive. For antibonding, the result will be like that. So at some point, plus and minus will be exactly the same. So the total will be 0. It will be 0 probability to see electron between two atoms. And square will look like this, touching 0 in the middle. This is how two hydrogen atoms will behave when we'll move them from infinity close and close together. So here distance is 7.5 angstrom, and electrons start touching each other. Blue is very low probability. Still you see that they are joining together, but atoms are sitting almost intact. Coming closer, there is some deformation of pinkish. Coming closer at 4 angstrom, you see the pinkish area is now joined together, and at 3 angstrom, red area is starting joining. At 1.5 angstrom, yellow starting joining. So atoms are very close, and this is a real hydrogen molecule. It's interesting that we're looking from large distance. It looks like one spherical entity, like one atom, not two. You may recall that in ideal gas model we have all gases being spherical. Anyway, there is of course some difference in electron density between these two hydrogen atoms. Let's draw the energy diagram. For hydrogen 1 we have electron at 1s orbital, and exactly the same picture is for 1s. Now, orbital that is symmetric, we'll name it sigma, similar to s. Sigma is Greek equivalent, and because it's made of 1s, we'll label it sigma 1s. Here we have two electrons, but now they should have opposite spin. You remember Pauli principle? At one orbital, electrons should have opposite spins. Total spin is 0. So there is no magnetic moment for this. Electron configuration will be sigma 1s squared. And the energy will go down because this orbital is energetically favorable. Anti-bonding orbital here will have practically the same energy but unfavorable. We'll name it sigma star. Let's look at energy diagram of the same. So for bonding at large distance it will be some attraction, so favorable energy, and this will be the distance for real hydrogen molecule. If we'll start pushing hydrogen atoms even further, the energy will be less favorable, and at some moment it will become unfavorable because positive nuclei will repel each other. So our hydrogen molecule will sit here. With anti-bonding orbitals, with electrons and anti-bonding, you'll have no attraction at all. At any distance, you will have only repulsion between them. So when two electrons from two orbitals overlap with each other, making one sigma bonding orbital, and there are two electrons occupying of this orbital, we say that bond order is 1, or we have a single bond, hydrogen, line, hydrogen. Single bonded orbital we usually depict as straight line, 2 electrons, 1 line. Now, what happens if we'll put only 1 electron? It'll be H2 plus ion. Of course, it will be favorable because there are 2 H pluses and 1 electron between them. But bond order will be 1/2. Energy will be roughly twice smaller. Configuration is sigma 1s 1. Okay. Now, what if I'll take one more electron in addition? How it's possible? If I take helium atom that has 2 electrons at 1s orbital and another helium ion that has only 1 electron at 1s orbital. Now I have the same 1s system, so sigma 1s and sigma star 1s. But I have 3 electrons. So 2 electrons are occupying bonding, 1 is occupying anti-bonding. Total bond order will be 1 minus 1/2, total 1/2. If I'll take 2 helium atoms with 2 electrons at 1s orbital each, I'll have 4 electrons total, so they will occupy sigma s and sigma star as well. Bonding and antibonding occupation is exactly identical, bond order is 0, which means there is no chemical bond at all. Now, what happens next? If we'll go beyond this point to lithium, a lithium will have core electrons, 1s, completely occupied. They will play no role in chemical bond. And we'll have one electron at 2s orbital. So if we'll bring two lithium atoms together, we'll have exactly the same picture with sigma 2s orbital bonding, and we can make lithium-lithium single bond. Similar to that, we can consider beryllium. Now, beryllium has two electrons at 2s, so it will behave like helium. It will be two electrons at sigma bonding and two electrons at sigma anti-bonding from the second beryllium atom. It will be no beryllium-beryllium bond. We can continue this consideration for other similar atoms. So let's make a summary. Covalent bond form when atoms share valence electrons in the region of space created by orbital overlap. It's symbolized by a line between the atoms. Now, it's important to understand that electrons are not sitting between the atoms. They are just two electrons participating in the bond. But electron distribution in atoms is very similar to how it was in atoms without chemical bonding. There is very little change in electron density between two atoms, but this change is sufficient to make strong covalent bond.